Check, check. Alas, here we are at the beginning of a new stream. What does today entail? We're going to be doing things like AC analysis of circuits. We'll look at the application of nodal analysis to AC circuits. And various things of that nature, don't get bored, right? Don't already leave the stream, but we're going to get into some science shit and some engineering. So, electrical engineering specifically, perhaps we'll get into some CAD later. I don't really know. I'm not sure where the night will take us and how long this is going to take because I need to make sure I know every bit of information, right, so that I can do the absolute best on, the various tests and things that the university brings forth. I need to be ready for every obstacle, prepared to overcome. Really it's all mental capacity. Do you have the fortitude to persevere and get through the electrical engineering hardship? Okay. So good intro. That was solid monologue for the intro. Ready for it all. Bang! Let's go. Okay. Dino's here. Dino's in the chat. My absolute favorite chatter of all time. Right? Dino is the best. Dino deserves everything I'm willing to give the world. Okay? I'm willing to give everything I have for Dino. So. Alright, well, enough of the sappy, bullshit. Let's get into the stream and the content. And let's see exactly what we're going to be working on today. Here's a transition right into our blank canvas. Okay, get into the Bob Ross feeling, Bob Ross character. Surely you know Bob Ross, Dino, of course, right? Famous, ultimate, absolutely famous painter of all time. Dino sends hearts. Beautiful, beautiful. I wonder, I know that guy. Yes, an absolute legend. Right. I know that guy, yes. Okay, what was I doing? Here we go. Okay. Let me pull up the work, pull up the problems, so that we can work a couple and get to know the equations intimately. We want to kiss on the equations and get real close with them. Yeah, the good equations, formulas, we love them. We love them so much. We're gonna get on them, and we're gonna stay on top of them, and we're gonna use them. Okay. So let me pull this up. So, World Cup, huh? So was that Dino, was that the final match? That was it. So Spain won everything? Or is it over? Or am I mistaken? Perhaps it was just that game that was the hype, and yet the tournament continues. I don't know, correct me. Spain final, that was the final match. That was the final, very final match is what you're saying. Or they're in the finals. See, I don't quite comprehend fully. That was the final, or they're in the finals? Okay. Alright. Final match done. Boom! Okay. That's amazing then. I know there was like a bit of a conflict there, right, between, two forces at hand. And, right, because there's this association. Spain won with 1 point against Argentina. 1 point? Ooh, I didn't know it was that close. That's incredible. Right, there's this feud, quite a bit of tension in between the teams. But cool, that's awesome. Not necessarily between the teams, but I mean the fans, right? Because it's an ideology. Not an ideology, actually. It's more like a good versus evil type of thing. Actually, I mean, come on, let's not kid ourselves, right? All right, I'm finally getting it pulled up. This take me hours, right? Okay. We should go back to this one because I actually didn't really know. Yeah, I didn't know exactly what I was doing. I've since become more competent, but like, there's still one portion of it that I don't fully understand. the inductive reactance, the impedance of the inductor. We did that one, and that one's simple. That one's simple. That one's simple. We did that one. Okay, so let's do this one. This one I also do not really know how to do, so let's get into it. Alright, if my thing could focus here. There we go, something like that. Come on, buddy. Come on, buddy. There we go. You know, really pull that Bob Ross out, right? Just a cute little resistor right here. And another one just right here. That's really nice. And another inductor here. Look at those coils. Absolutely magnificent. And we're just going to put a little magnitude of 50 nanofarads here. And then a 1.2 kilo ohm capacitor, or resistor here. Fuck Bob Ross! I lost it. Love the cute circuits. Why is it cute? This is deadly. This is running severe amounts of amps. You know, the current is ridiculous on this bad boy. It could kill you. Cute? Are you kidding me, Dino? Dino's cute, though. Dino's very cute. Okay, let's get a bedroom. Right, who said that? What? Okay. Come on, quit fucking around, guys. Quit fucking around. Alright, IG. Negative V out. 5K. Kilo ohm. That's 5,000 ohms if you didn't know. Oh, rhyming. 200 millihenry. Oh, no, can you... There we go. 200 millihenry. And 15 nanofarads. Circuit kind of looks like shit, right? You can't read that. Oh. Let me... Wait. The circuit wasn't bad, but my labeling was awful. I wasn't even paying attention to that. Sorry. Let me do better. What's this one? 1.2. Yeah, that's better. Is that even readable, though? That might be kind of small. Oh well. Moving forward. Okay. So the question at hand, right? The frequency of the source voltage in the circuit is adjustable until V0 is in phase with IG. What is the value of omega in radians per second? What is the value of omega in radians per second? I don't know. Okay, I don't know. I mean, I've made an attempt to solve this before, and you know, like I added up impedances. I got the total impedance and things like this. But that still wasn't right. Okay, here we go. My stream wasn't showing up on Kick. Alright. Okay, here we go. My stream wasn't showing up on Kick. Far. Yeah, that circuit's a little small, right? Sorry, guys. Let me draw it bigger. Yeah, that circuit's a little small. Oh, okay. Right? Now I got it. Sorry. Too loud. Okay. Alright, let's do this better. That's a little baby circuit. You're right. It is cute. Let me fix this. I don't want him to be cute. I want him to be scary. Let's turn it up a notch. Okay. For the stream, you guys can't see that shit. Okay. Let's go real big time. Alright, that's better, yay. That's better, yay. Nah. That's better, yay. I think that looks a whole lot better there, eh? Okay. So we know this. Alright, so what? Should we find the total impedance? Is this what we should consider? Okay, let's just do it. Let's see. What do I want to know? Well, we could define it as a ratio, and then what are we asking? Omega in radians per second. We're looking for omega. It really has nothing to do with that, right? It's more of a frequency thing. Okay, well, if we were to consider the two elements which frequency is applicable to, right, we'd look at the capacitor and the inductor. So must we take only these two into account? The capacitor is directly across, directly in parallel, so it won't be affected by the resistance. So that should be like a pure, okay. And then what? The capacitor, XC, the reactance, equals -1 over omega C, right? And then ZC, if we're looking at the impedance, equals -J over omega C. J is our imaginary number, right? So then, or that could be the case. Okay. Where do we ever take this now? Right? Where do we take this now? So, considering all of the things that I don't know, because it'd be too many to name, let's consider what I do know, because it's a lot less, right? So, alright, I know the values of these, right? I know this is what's happening here as far as our capacitors in parallel. I'm kind of like, let me just put this into this AI thing real quick and ask it a question. Let me just ask it a question, just a little question, and then I'll tell you exactly how to do this because I know. Find the value of omega in radians per second for the output voltage V0 to be in phase with the current source, or source current IG. The total admittance Y of the parallel network connected across the current source must be purely real. The imaginary part must be 0, right? And we figure that because it's in phase. Right, and if it's in phase, then there is no imaginary part because that is the phase shift due to the reactance. Okay, the reactance, which is the variable x as we have labeled here. Okay, let's go ahead and apply this into, let's do an application of this. So it says y1, right, this is our admittance. y1 equals 1 over 5,000. Okay, right, talking about this guy. Y1, the admittance of this branch right here. Very well. Okay, equals 0.2 millisiemens. 0.2 millisiemens. That's your first time hearing the unit of Siemens. Okay, it's a unit of conductivity. All right, chill, bro. All right, pause. Okay. All right, RL branch. This guy right here is looking at Z2. Okay, we're going to define it by its impedance. Why not its admittance? Why the impedance now? Because we do it there. Okay. First, define the impedance R2 plus J. Okay. R2 plus J omega L, right? Because that is the impedance of our inductor. As we define here the impedance of the capacitor, we can go ahead and define the reactance of the inductor, omega L. And then the impedance of the inductor equals that imaginary number multiplied by omega L, right? Multiplied by the reactance. Yeah, that's right. Yeah, reactance. Bang! Yeah, that's it. Okay. Cool. All right, I appreciate you guys listening in. Let's really fucking take it home. Let's hit a home runner, and let's we're gonna go beyond the fences. We're gonna explore new horizons, and we're gonna shoot for the stars. Okay. Even during the daytime. All right. So. Okay, that's going to look like this. It's going to be, if we plug in our values now, it's going to be 1200, right? 1200 plus J omega 200 milli. So J omega multiplied by 200 e to the -3, right? That's milli. Okay, so like that. And then now we have our complex equation. And to find the admittance, right? Oh, Z2, Y2. We're just going to take the inverse of the impedance, and that's going to look like 1 divided by this complex equation plus j, oh wait, 200, 0.2, right? Right, 200 milli. 0.2 j omega. Like that. Okay, can we see that? We can see that. It looks okay. It's not beautiful, right? Because my handwriting is shit, but that's okay, okay. Don't judge me by my handwriting. Or, okay, perhaps do. Perhaps do. Perhaps. Let's fix it. Yeah, that's much nicer. Okay. Y2. And now y3 is going to be the inverse, or it could be positive 1 over j omega c. So we can do positive j omega c, which c is 50 nanofarads, and that's going to look like 5e to the negative 9. Oh no, I'll have to write it. How do they write it? Right, and then y3 equals, yeah, exactly, jw, yep, okay. Where's my calculator? Let's type in this inverse equation right here, this inverse function, and I thought it was in here. No, I gotta get it. I'm so much better with my calculator. Alright, I'm so much better. Don't leave. I have to get my calculator. Don't leave. I'll be right back. Okay, fucking time me. I just felt, oh, it is. Okay, time me, go. Alright, I'm back. Oh, I didn't need to put this on. Yeah, that's right. Chattery cat. I like it. Ooh, ooh, wait, that has another meaning too. Or, sounds like it. Okay. Alright, I appreciate you guys staying. Thanks for hanging out. Send some hearts. I'll send some hearts to you. Unmute. I never muted. I'm not muted. No, you're fucking playing with me. You're playing with me. That's funny. That's really funny. Okay. Oh, I'm playing. Yeah, trying to pull a quick one, huh? My bad, yeah. Alright, back into it. Everybody pay attention, alright, because it's gonna take, you can't fuck up one time. You fuck up, you lose everything, okay? Your whole equation's gonna be wrong, and you're gonna have the wrong answer, and then your bridge is gonna fall apart, your airplane's gonna crash. What's with the smug chat? What's with the smug chat right here? Are you kidding me? What is this? Are you kidding me? That shit out of here. Okay. Oh, it would only work. Oh, it didn't work. I was looking at a different screen. Oh, that's so fucked. I really fucked that one up. Okay. So now we consider these things. Set the total imaginary part to 0. Well, after adding imaginary y. Okay, so all the imaginary parts. Anything consisting of j. So if we did imaginary y, right? We found that one. Oh yeah, we didn't do that yet. Let's calculate that. So 1 divided by 1200. Yeah, I don't know why that happens. Let me give it something to focus on. 1 divided by 1200 plus, nope, 0. I need one more 0 plus 0.2 I, and that's it. 1. Wait, I don't know if I can just like plug that in. Wait, let's see here. That's how you do it. Okay. Alright, so we're gonna do what's it called? Shit, I completely forgot what this method is called. Where we do the conjugative. Oh no, help me out here, Dino. But we're gonna go ahead and multiply this function, right, by its opposite. So 1200 minus 0.2 j omega, right? Because we want to get rid of that middle term, and then we're also gonna multiply the top by the same thing, right? Because essentially, like, we're multiplying by 1, so that we don't change the equation. But, alright, so we're going to do this. Alright, so this is going to come to y2 equals 1200 minus 0.2 omega, right? Shouldn't we do this one too? Let me see. Yeah, that's good. Alright, 1200 times 1200 is 1.44 million. So 1.44 e to the negative 6, or nah, not negative, but e to the 6. Dino, what does that mean? That's not helpful. Your emojis are not helpful whatsoever, Dino. I appreciate it. No, I really appreciate you. But the emojis ain't helping, Dino. Shit. But yeah, okay. Alright. Thank you, Dino. Alright, e to the 6. Now what? So now, right, and those terms are gonna cancel, so we're just gonna do negative 0.2 squared. J would be a negative 1, so that'd be a real number. And wait, are we gonna cancel? 1200 times negative times positive, it would cancel. And that's a real number. So it's all real. It is. It's all real. Yeah. Okay, so negative, yeah, times a negative. Alright, we're gonna square it, so it's gonna become plus. Shit. Plus 0.04 omega squared. Yeah, omega squared. I don't know why I wrote it there. J omega. Okay, now we have our y2. So now if we add up all the admittances, right, everything's in parallel. Then we want to set that to 0. And then we want to solve for omega. The total imaginary part to 0. So if we did that y1, there's no imaginary part. Y2, there is an imaginary part. It would be negative 0.2 j omega divided by 1.44 e6 plus 0.04 omega squared. And y3, imaginary part, is entirely imaginary. Plus omega 5 e negative 9 equals 0. Alright, that's purely imaginative. Imaginary. Purely imaginary. What the fuck? Okay. Yeah. Okay, and we can get rid of the... Right, we can get rid of the j, the imaginary number. Okay. And then we solve for omega, assuming omega does not equal 0. Okay, solve for omega. Alright, so just the imaginary part we set to 0. Okay. So let's go ahead and put this on this side. So negative omega 5e negative 9 equals negative 0.2 omega divided by 1.44 e6 plus 0.04 omega squared. Let's see here, we multiply this. So negative 5 e to the negative 9 times 1.44 e to the 6. Negative 0.0072. Let's see, omega, right? And there's no omega in this term, right? Because we're just going to multiply this whole term to this side of the equation. And then we're going to use the law of distribution, okay? That's the plan here. So that's what we're doing. So we did that. We distributed 5e to the, well, negative 5e to the negative 9 into this equation here, this function. So now we have, so we did those, and now we're going to multiply 0.04 omega squared and multiply by this. So negative 5 e to the negative 9 multiplied by 0.04, yeah, minus 2e negative 10 omega cubed equals negative 0.2 omega. 0.2 omega. Okay, we did that. Alright. Now we can divide by, we can get rid of one of the omegas. We can pull it out of everything. Those are gone. So now we have 0.0700072 omega. No, that's gone. That one's gone. That canceled. Minus 2e negative 10 omega squared. And then we're going to pull him to this side plus 0.2 equals 0. We're going to add those two. So we have negative 0.0072 plus 0.2. I mean, it's going to be, yeah. Okay, 0.2 negative. Okay, that's going to equal 0.1928 minus 2e to the negative 10 omega squared equals 0. Okay, very well. So we can add that to that side, and then we can divide by 2e to the negative 10. So 0.1928 divided by 2e to the negative 10. Omega squared equals 9.64. What is that? 1, 2, 3, 4, 5, 6, 7, 8. E to the 8. Radians per second squared. We'll square root it. Omega equals square root of, oh shit, omega equals 31. Wait, that's not right though. What the fuck? It's not right. How's that not right? Shit. Okay, let me run it back. How's that not right? Let me run it back. Bear with me. Bear with me, okay? Holy shit. Alright. That was a lot of shit going on there. I mean, it wasn't ridiculous. Is it this? Are you sure that's correct? Let me calculate that. There's no fuck. There's no way. There's no way. Alright, let's get rid of all of it. I guess practice makes perfect, right? Practice makes perfect, okay? So, I ain't even tripping. I'm not tripping about it. It's fine. I'll just erase everything. It's no worries. It's no worries at all. Yeah. Yeah, it's no worries at all. I appreciate you guys being here, though. I love you guys. Alright, I really appreciate it. I hope I can help you learn something. Or maybe, you might actually lose brain cells watching. But, at least we're in it together. Alright, thank you for being here. It's really nice of you. All right. So let's ensure that all of this is correct. That's correct. It's just simply the inverse. 1 divided by 5,000. Can we see that? Yep. 2e negative. Yeah, that is correct. 0.2. Yeah. Wait, did I add 200? See this 200. Wait, where'd I get that from? Oh, okay, this gotta be my problem right here. 200. That's not correct. But it's 0.2. Did he say 0.2? Is that correct? Yeah, so I think like you know, I confirmed that this is correct, but I think the computer was putting it in as a point two, as in like 200 millisiemens. But I mean, we're not even anywhere close to that, right? Wait, Y1 Z2? No, this is entirely different. This is this referring this 200 milli. Yeah, so that's 0. 0.2. Okay, never mind. No, 0.2, 0.2, 1200. This one. Yeah, we confirmed that. We did that. 1.44 E6. And that was 1.44 E6. 1.44. That's, yeah, 36 plus 0.04 omega squared. Okay, where did we go wrong? Right, we add all these. Software mega. Okay, so let's rewrite this. Wait, so. Yeah. Plus, right? Yeah, plus. Y2, Y3, Y3. 5e negative 50, 50, 50, 50. Come on, guys, 50. That's my issue, 50. Alright, that was literally it. Okay. So now this equals 0. Alright, let's do it again. So negative 50, omega 50, e to the negative 9 equals negative 0.2. We don't need the j anymore, the imaginary number, because we're in that realm. We don't need to add it. 6 plus 0.04 omega squared. We're going to multiply that. That's going to look like this. Negative 50 e to the negative 9 times 1.44 e to the 6. Bang. That's going to be negative 0.072 omega minus negative. It's going to be another minus. Negative 50 e to the 50 e to the negative 9 multiplied by 0.04 2e negative 9 omega cubed. Yeah, omega cubed equals negative 0.2 omega, right? Divide by omega, add 0.2, negative 0.72 plus 0.2. Actually, we move it to this side so we could solve for him. So we'll just add him. So negative 0.2 plus, is it 0.2? Yeah. Well, I guess I'd have to do a minus. Minus negative 0.072, negative 0.128. Omega squared at this point, because we divided out. The math is the fun part. Absolutely, the math is the fun part. Can you not see? Oh yeah, you can see it still. The math is super fun. Squared. Negative 2e negative 9 omega squared equals what we just do? Oh, negative 0.128. Right. Okay. So now we divide negative 0.128 by negative 2e to the negative 9, and then we're gonna have to take the square root of that. But let's do this first. Divided by negative 2. E negative 9. Okay, so we get, what is that? 3, 6, 64 mega, or e to the 6 equals omega squared, and then we're going to square root, and omega equals, this is our angular velocity. Well, what would we consider angular frequency? I think 2 pi f, right? Angular frequency, yes. Okay, so this is our angular frequency. Again, taking the square root of 64 million, we have 8,000. and that's radian per second is our units. All right, fantastic. So, okay, to make everything real and to cancel the imaginary part so that we don't have any reactances, right? Okay, so that was the problem. Yeah, we have one more thing though. Is phase. Okay, so right, so V naught is in phase with IG. Okay, so that was the parameter, that was the restriction, right? That was given, the constraint rather. Let's consider it that. Let's define it as the constraint. The constraint that was given was that V out is in phase with IG, right? V out right here is in phase with IG. And now, this is the voltage of the current source, okay? So for these two to be in phase, that must mean that all other components in the system appear real, right? There's no, all their impedances appear real, right? Because if we're looking at inductors or capacitors, they have in parts of their impedance, as which we denote as Z, parts of their impedance are imaginary, right? They are considered reactances, and these are things like, these are methods of describing their energy storage capabilities, right? So they have a conservative energy where they store energy and give it back to the circuit at various points in the power cycle. So, and this is what we use the complex numbers and the imaginary numbers to represent, are these like storage elements, right? Or these storage properties of these components, those included being the capacitor and the inductor. So it's really cool. It's very cool properties, and so we have to take this into consideration when we're doing when we're considering power calculations or when we're building the circuit for particular frequencies, okay? And again, the problem for this one was that we had no phase shift whatsoever. Therefore, that would mean that no part of it was imaginary, and we calculated for a real part. That's why we set the imaginary portions of these various equations here equal to 0, because we didn't want them to have a value. Okay, right, so that's the whole purpose of that one. Okay, if IG equals 2.5 cosine omega t milliamps, so let's write that down. So now we have a value for our or our current supply, our independent current source, and that is, again, IG equals 2.5 cosine omega t, 5 cosine omega, sorry, I'm getting too far over. (2.5 cosine omega t milliamps), right? We gotta make sure we're using the right units, milliamps. Okay, where omega is the frequency found in A, which is 8,000 radians per second, what is the steady state expression for V out? The steady state expression for V out. Okay, IG, so V out, steady state expression for V out. Right, we found the radians per second, so I think it would just be the so with respect to admittances, V out equals, through Ohm's law, it would be then Y divided by IG, or IG divided by Y, because typically it'd be resistance, right, or in this case impedance multiplied by the current to get the voltage, right, Ohm's law. But now we're dealing with admittances, which is the inverse of impedance. Okay, so admittances, we're going to divide IG by the admittance, right? This would be the inverse of resistance. So IG divided by Y. I believe this is correct. Yes, yeah. Because V out would be proportional to IG, and that cannot change. Okay, that's it. So now, considering that, let's add up the real values of the impedance, or the admittance, which part of it is 0.2 millisiemens, 0.2 E negative 3 plus 1200 divided by 1.44 E 6 plus 0.04 multiplied by 8,000, right, omega squared. Okay, so that's good. And equals, well, yeah, we're just adding these. So equals 0.2 e to the negative 3. Can we see that? No. Here we go. Oh yeah, we're doing some math. We're really digging into it. I appreciate you guys being here. Hell yeah, give me a follow. We're gonna be working on some projects. This is me just doing my homework. This is more like obligatory. I have a really grand project that I'm working on, building a robot, and we're gonna have to implement a lot of different systems such as mechanical and electrical. That's probably the extent of it, right? We don't want to introduce any pneumatic or hydraulic systems. Those are quite power hungry. They consume great amounts of power, so we're going to stay away from that stuff, and we're going to use electrical, and we're going to probably, I'm looking to supply it with a battery, although I do have the option to supply it with AC current source, such as a wall outlet, and you have many of them outside your home because this is going to be applicable to residential homes, right? We're going to be doing grand shit, okay? We're going to be doing amazing stuff. We're going to be building a lot, innovating and inventing and doing all sorts of different things. All right, let me chill out now. Sorry. Okay. Yeah, we were solving for this. So plus 1200 divided by 1.44 e to the 6 plus 0.04 multiplied by 8,000 squared equals 5e negative 4. And again, this is milliamps. That's not what I'm doing though, just the admittance. 5e to the negative 4, admittance, Siemens. Was any part of this milli? 0.2, yeah. So I did account for that. Okay, so Siemens. Okay, fantastic. So now we take IG. So 2.5, and there's no phase shift, so we don't have to worry about that, right? So we just take the magnitude, 2.5 divided by 5 e to the negative 4. That's going to give us 5,000. Nah, I must have missed something. Wait, right? 2.5. Whoa. What did I missed something big. I missed something real big there now. Because I didn't change it into phasor form. And what's V out? That would be accurate. That would be accurate still. Let me think. Did I mess some up? Maybe this expression? No. Milliamp. 2.5 e to the negative 3 divided by 5 e to the negative 4. What happened? Oh shit. Okay. Yeah, because it's milliamps. I forgot to introduce that. So it's the milli aspect of the amps divided by now our admittance of 5e y here. I'll put y equals 5. Y real. I don't know how to denote that. How do you denote that? I don't know, whatever. Okay, 5e to the negative 4. 5e negative 4 equals 5. Okay, that's it. So V out equals 2.5e negative 3 divided by 5e negative 4. Shit. Amps, Siemens, equals 5 volts. V out of t equals 5 cosine omega t volts. Alright, fantastic. There it is. Bang! There it is. Alright, appreciate you guys. Thank you. Thank you for being here. There it is. Oh, wait a second. Oh, we have a value for omega. So hold your horses. 8,000 T V. There we go. Now that's complete. Now that's complete there now. That's a good looking equation there. That's a real good looking equation there. Let's move on to the next problem there now. That's a real good looking equation. That's a real good looking equation there now. If I say so myself. God, we can't see that. Let's just flip it around. There we go, that'll work. Alright. Microfarads and 240 ohms. 40 ohms. Okay, and then we're looking at V positive, V out right here across this resistor. Negative Ig, and we have find the steady state expression for V out in the circuit if Ig equals Ig equals Phi G equals 200 cosine 5,000 T milliamps. Milliamps. Yes. Okay, and the voltage across this resistor. Yeah, so we're just going to use a circuit or current dividing equation, current division equation. So let's first calculate all the impedances of, the total impedance of our two branches, right? Because our current's going to split here and here, and then these two series elements, these four series elements in their respective branches will feel the same current, you know. Okay, so we have 240, right? And again, they're just in series, so we're just going to add the impedances. Impedance of the resistor is 240 ohms. Of the capacitor is J, negative J, and it's a negative, so minus J divided by omega, which what is omega is 5,000 J 2.5 e to the negative 6, right? Because we have microfarads. All right, like that equals, and then this one's gonna look like 80 ohms plus omega, again 5,000, so J 5,000, which is our omega, multiplied by 48 e to the negative 3, that's millihenry right there. Okay, so we'll go ahead and calculate that. I mean, this is just going to be our, right, so it's a complex equation, right? So we're just going to have our two various portions of the equation, which is going to be our real and our imaginary. So those will be separated by the imaginary number J, or rather mathematicians like to use I, right? So J is more of like the engineering, use, whatever. Okay, So 5,000 multiplied by our capacitance of 2.5 e to the negative 6 is 0.0125. That to the, or 1 divided by that. Oh, I didn't mean to add j down here. Is 80. So this equation looks like 240 minus 80j. Okay, we'll do it like that. And then this one looks like 5,000 multiplied by 48 e to the negative 3. That looks like 240. So this looks like 80 plus 240j. Interesting. Very interesting there now indeed. Look at that. Look at how that maths out. Look at the math is mathing. The math is absolutely mathing, and I appreciate all of you being here. Thank you very much. We're gonna build some crazy shit. We're gonna take over the world, okay? In my opinion, allegedly in my opinion, okay, for legal purposes. Alright, we have our two equations. What was I doing? Oh yeah, so we're gonna just do a voltage or current divided formula, and then we're gonna figure out the current in this branch, and then we're gonna take that and multiply it by our resistance to get our V out, right? And then we know that it's a resistor, so the current is in phase with the voltage, so we don't have to worry about phase because it's a resistor. Whew. Alright, I hope this is informational for you and you can retain some knowledge. If you want to take some notes with me, please, let's do it. Just put it in the chat. Say, hey, you're moving too fast and I'll move faster. Okay, hey, you're moving too slow and I'll end the stream. Okay, so let me know how you're feeling. Alright. So now we did that. Okay, now the current division equation looks like this. Current divider formula, IG. So IG is 200 cosine 50t. Let's put this in phasor form also. So if we had cosine, and so it's going to depend. Is the phase going to depend upon that? Oh, wait, actually. Well, okay, so phase form. So IG, I think we denote it by a capital also. It's a capital. So IG equals 200 cosine 5,000 t milliamps. So we don't have a phase, but it's the phase shift with respect to the component. So there isn't a defined phase here, right? It would have been stated omega t plus phi or phi plus phi. But we don't have a phi defined, so we don't have a phase shift. So I think it would just be 200 phase 0 degrees. Okay. Yeah, that's how we'll denote it. Okay. But then when I do that, is that going to be necessary? So imagine we had 200 theta multiplied by, okay. So we're going to go, we want the current through this branch, so we have to do this in the numerator. So, and that's 80, where are we at? 80 plus 40, yes, this one. So 80 plus 240. J, and then the sum of these two equations, so that's just going to be 240 plus 80. 240 plus 80, which is 320. Yeah, I know, okay. 320, and then negative 80, 240. Plus 160 j. So like that. Okay, we can go ahead and calculate that ratio. All right, so that's gonna equal 200 phase 0 degrees. But that's the thing. Do I need to add the phase in here right now? Because I don't have the phase of any of the components, such as like the capacitor is gonna lag by, well, okay, depending on what we're talking about, but it has a phase shift of negative 90 degrees. Okay, the inductor has a phase shift of positive 90 degrees. Alright, so do I need to add these? Let me see. Let me ask AI a question. You can come with me. Okay, let me see. Let me get back to my display station. Okay, let's ask AI a question. Alright. Hello, good sir. Right, good sir. Right, give some common courtesy. You know, I think he'll really appreciate it, and I think he's gonna answer our question with full disclosure. So, you know, just be a nice guy. You know what I mean? Okay. What we're gonna ask? Okay, so we have it in a rectangular form. Yeah, we have a rectangular. Okay, so hello, good sir. I am doing AC circuit analysis, and I performed a I performed a current division formula using the source current and 2 impedance branches. Considering my source does not have an inherent phase shift, must I add the phase shift of components like capacitors and inductors when considering their branch impedance. You absolutely must include the phase shifts, the imaginary parts of the capacitor and inductors when you calculate branch impedances. When analyzing AC circuits and phasor domains, treating components like simple real numbers will lead to incorrect answers. Here's exactly how and why you must include them. How do you include the phase shift if you have a resistor in parallel with capacitor? Bitch. Let's see. Wait, use the standard product over sum formula, keeping the imaginary units intact. Oh, this requires more than I thought. Okay. Shit. I was almost cooked. This requires way more than I thought it would. Okay, that's well, I guess we're learning. We're learning together. Right. All right. Identify individual impedances. First, write down the impedance of each component as a complex number. Purely, yep. XC equals 1 over omega C is the capacitive reactance. Yep. Apply the parallel formula. Use the standard product over sum formula, keeping the imaginary units J intact. Z equivalent, ZR times EC, ZR plus ZC. I said parallel? Bro, no. How do you introduce the impedance or the phase shift of a capacitor if you have a capacitor and inductor, capacitor and resistor in series? And I said parallel. I'm really fucking up. Right, so purely imaginary negative 90-degree shift. Right. R squared plus, okay, die. I'm stupid. I really am stupid. Shit, I don't think I should have showed you that. Ooh, phase shift looks interesting. It absolutely is, my sweet dino. My sweet dino. Alright, enough of the musical shit. Okay, let's get back into the circuit analysis. I know what to do. Okay. Alright, so let's put these guys, oh yeah, that's why it would be needed. Yeah, because we're doing a multiplication. Okay, now it all makes sense. Okay. Alright, so this is a rectangular form of the phase form. It's the rectangular form of the phase form. The rectangular, form for the phase form. Whatever, that's a fine way to say it. So let's put it in polar coordinates. Let's put it in polar form. And so that's going to be like the square root. Okay, so the square root of 240 squared plus 80 squared. And then our phase angle of inverse tangent 80, negative 80, divided by 240. Okay, and this equals 240 squared plus 80 squared. So a magnitude of 252. We'll make that 200. We'll round it to 253. Whoops. And then angle, phase angle, inverse tangent function of negative 80 divided by 240. Negative 18.43. And if you're doing this at home, make sure that your calculator is in degrees, right? Because you have a degrees and you have a radians mode. So make sure that you're consistent with your modes. All right, whatever you're calculating. Okay, you can't do. Don't be in fucking radians and expect to calculate cosine or a sinusoidal function in degrees. It's just not gonna work. You're gonna get the wrong answers. You're gonna be like, what the fuck is going on? Okay, we don't want that. All right, we want cool, calm, and collected, at peace and content. Okay. I hope that this is what you have in life. Okay. I hope that you're content and you're happy, and I hope that you get all that you deserve. Work hard and push yourself to your limits. You might just surprise yourself. I would believe that you do not know what you are capable of. Okay. So we calculated that one. Let's move on to the next. So square roots of 80 squared plus 240 squared. Okay, it's the same thing. Inverse tangent guy of 240 divided by 80. This will be different though. 240 divided by 80, and it's positive. Whoa. 240 divided by 80. Oh. 240 divided by 80 equals 253 phase. Positive 71.57 degrees. Okay, beautiful. Isn't the math just mathing right now? I mean, come on, how more satisfying does it get? Okay, the math is just absolutely mathing right now. Okay, it's good. It's really nice. Look at that. It's beautiful. I'm writing a little bit better. It's a little bit more organized. Before it looked like shat, and I'm sorry for that, okay? But now we're writing in a succinct, beautiful, organized manner. My script is Times New Roman, okay? Isn't so nice. All right, wait, what are we doing? We did that, so I think now we can calculate this. Oh, except I don't want that. Wait, 80 plus 240. Okay, I only want this. And then now I need to calculate this in order to do the multiplication. So let's do one more. 320 squared plus 160 squared. Inverse tangent of 160 divided by 320. Okay, equals. So let's do the square root. 320 squared plus 160 squared equals 357. That's the magnitude. Let's round it up to 8. 358. Okay, phase angle, inverse tangent, 160 divided by 320. 26.57 degrees. Okay, beautiful. 160 divided by 320, correct? Yep. Okay. 320. Okay, that's good. That's good. So now, that's very nice. Okay, now we can go ahead and do this multiplication. Okay, so 200. Oh, yeah, I have all the degrees. Yeah, okay. And look at how the resistor, so a purely capacitive element would have a phase shift of negative 90 degrees. A purely inductive element would have a phase shift of positive 90 degrees. Now look at the contribution that the resistor makes, like the real part of the impedance makes to this phase shift. Okay, so it's very vital and it plays a large role. And now the reason I converted it into polar coordinates is because when we're doing addition, like earlier when we're doing addition, we need to do addition in rectangular coordinates, okay? And then when we're doing multiplication, such as we're about to do here, we're about to do a division right here and a multiplication here, right? We have to do things in polar coordinates. It's simply just the way that it has to be. All right, so that was the reason of our conversion, though. I want you to understand that. Okay, so we got that. So 200, 0 degree phase shift multiplied by 80 plus 240, which was, yeah, this one, right? 80 plus, yeah, this one. So 253 phase 71.57 degrees divided by 358 phase 26.57 degrees. Okay, equals 253 divided by 358. So 200, 0 degrees, 0.706. We'll round that up to 7.07. Multiplied by, so the way that we do phase, or like phase angle, multiplication or division, is kind of like synonymous to logarithms almost, right? So it's going to be theta 1 or minus theta 2, right? So like 71.57 minus 26.57. And if it was a multiplication, then it would be an addition, you know? It's just vice versa like this. Not vice versa, no, just like opposites essentially, right? Okay, so that's going to look like 71.57 minus 26.57, 45. How interesting. 45, 707 degrees, 200 phase 0 degrees. All right, so if we were to do a multiplication here, 0.707 multiplied by 200 equals 141.4, and then it would just be an addition of 0, so the angle is still going to be 45 degrees. Okay. And that's the current amps. Is it really so large though? Shit, did I miss something? Milliamps. I probably did. Yeah, 200. This 200 here is milli. So it's probably just milliamps. Yeah. But that's really important. The units are super important, but it's probably just milliamps. Milliamps. Okay. Hopefully. So that is our current I1. That's our current I1, I2, I1. Okay, now if that's true, then V naught equals, as we have denoted here, V naught across the resistor. V naught equals our current, 141.4, phase 45 degrees, multiplied by our resistance of 240 ohms, which has no phase shift, 0 degrees, 141.4 times 240 equals, 141.4 e to the negative 3 times 240 equals negative 130. Wait, what? 141.4 e to the negative 3 times 240. Yeah. Okay. 33.9. Yeah, well, 33.94. We'll do it here, around it there. 45 degrees. Volts. Okay, and then now wants it in back into a time dependent, which is like we have phase form and then frequency form. You know, this is our original current, which is in like this, you know, omega t form. And that's like, what is the proper term for it though? I don't know. You know, this is phase form. This is the phase form we're working in. This is rectangular phase form. This is polar phase form. And then this is like time dependent form, time form, transient form, some shit like that. I don't know. But anyways. Okay. So that is correct, but let's convert it into our time form. So V naught, that would actually be labeled as V. Yeah, that'd be labeled differently. That should look like this. Be capital V. So should this. Phasor form usually is denoted differently. Capital I, 1, we'll call it. Okay, but there we go. V out equals V out of T equals 33.94 cosine. We know omega is 5,000. It's the same 5,000 t plus 45 degrees volts. And there you got it. Bang! That's the answer right there. Beautiful. I appreciate you guys being here. Thank you for joining, tuning in. Look at that. Isn't that gorgeous? Look at the mathematics and, essentially all of this work for like this little circuit. I mean, really it is quite a small circuit. But it's still necessary, and we're doing calculations or arithmetic, complex numbers arithmetic. Yeah, I don't know. Let me know what you think. Send a couple chats. Let me know what you think. That's good. All right, there's that problem. Let's move on to the next. Let's keep rolling. I think we're feeling pretty good about it. And then we can even get on. We have we have one more question. So 2 more questions, and then we get on to essentially a new subject, right? We're going to be still utilizing the same things that we're doing here, but it's going to be entirely different problems where we're doing an actual circuit analysis. This is just kind of being familiar. There's some circuit analysis that I've done here, but this is getting familiar with the impedance and the admittances. Next, we're going to move on to actually solving circuits. So, like here shortly, if I continue till then. We'll see, though. But I really appreciate you guys being here. Thank you for tuning in. Let's fucking get it done. Let's go. All right, that looks nice. I kind of didn't utilize all the room on this page. I still have some more. Should we just drown it? Should we just drown the page? Alright, yeah, let's do it. Let's just drown the page. You know what I mean? Okay. Use the concept of the phasor to combine the following sinusoidal functions into a single trigonometric expression. Okay, so this is probably going to require some transitions, perhaps. Let's see. So the first function is this. Can you see that? Yes. Y equals 100 cosine 300t plus 45 degrees. 100 cosine 300t plus 45 degrees plus 500 cosine 300t minus 60 minus, whoops, that was bad. What time is it? 9:19. That's great. That's really great. My phone's about to die though. Ba-dum-bum. My phone's gonna die. Okay, minus 60 degrees. There we go. Okay, and what is the question? Combine them into a single function. We have a cosine, we have the same omega, so it's just as simple as, an addition. Yeah, we can just literally combine them, can we not? Let's see, so 100 plus 500, so equals 600 cosine 300 t 45 minus 60 negative 15 degrees. Alright. Y equals, oh shit, no, it's not that simple. What the fuck? What? Wait, cosine. I guess it's not that simple. Really? Alright, I have to convert them into phase form. I mean, that's fine. We can do that. So, is that just like, really? Is that necessary? And then what if I do that and it's still addition? So rectangular form. So we have to do all that. Interesting. Okay, so, well, I don't know, 100, 45 degrees. And then we have 500, for 60, negative 60 degrees. So, yeah, we can do that. Okay, so, I don't know, we'll just denote it as like xy. X equals 100 cosine 45 degrees, which is square root of 2 over 2, right? 100 sine of 45 degrees, which is the same thing. Okay, that's our xy. Right, we need to get into rectangular coordinates in order to add it. 500. So again, x here is 500 cosine. Whoops. Cosine negative 60 degrees. 500 sine negative 60 degrees. Okay, now we have those. So the equations are going to look like this. So we have, oh, well, that's denoted as y. So I don't want to denote this as y. Let's just say yx, y, y. I'll call it that. And then so y in total equals, well, y1 equals, because we have these two equations in this one problem. Okay, let's look at this. So 100 sine, let's just calculate 100 times cosine of 45 degrees equals, and that's our real portion of the equation, 71 plus 100 sine 45 degrees. So, oh right, it's the same thing. Okay, so but this one's gonna include j, 70.71. That's what I mean by real and imaginary, right? It's our imaginary portion. So equals 500 cosine negative 60, 250, 50 plus, I don't know, maybe minus 500 sine negative 60. Yeah, it's a minus. $433 j. Whoops. Okay, so now we're just gonna, in order to combine these two equations, we're just simply gonna add them. We'll add their various components, right? The imaginary, and add the real component with the real component and of y1 to y2, and then add the imaginary component of y1 to the imaginary component of y2, right? We got to keep them distinct from each other. So 70.71 plus 250 equals 320.71 plus, actually minus, it's going to be a negative 70.71 plus negative 433. Oops, that was 4 there. Minus 362.29. Okay, right? There we go. Looking good, looking beautiful, looking... Okay. OJ. Alright, so now to compute the magnitude... Or, well, let's put this back in phasor form, and then we can convert it back into our time-dependent form, like above. Okay, so that's going to look like... y equals the square root of 320 squared plus 0.71. Let me sharpen this. $320.71 plus 362.29 squared. And then angle inverse tangent function of negative 362.29 divided by 320.71. Yeah, just like that. Just like that. Okay. Why? All right, so let's calculate these values. So square root of 320.71 squared plus 362.29 squared. Okay, that equals 483.85. Whoops, that's the magnitude. Why did it broke my lead. Look at this shit. It broke my lead. Are you kidding me? Absolutely redonkulous. Okay, where were we at? Oh yeah, so 483.85 phase inverse tangent negative 362.29 divided by 320.71. Negative 48.48 degrees. Oh yeah, we got to put it back into the other form. So that's going to look like y equals... Right, the angular frequency doesn't change, so cosine 300 t minus 48.48 degrees. Right, the angular frequency doesn't change. Okay, beautiful. There's that one. Let's move on to the next. Yeah, okay, let's use a new paper now. Alright, getting familiar with the complex numbers, the complex equations. We're getting into the game, and the game is game, baby. Alright, on to B. Y equals 250 cosine 377t 77t plus 30 degrees minus 150 sine. Okay, cool. We're gonna have to do a conversion here. Sine from sine to cosine. 377t plus 140 degrees. Alright, cool. So let's go ahead and do that right away. So y equals 250 cosine 377t plus 30 degrees minus 150 sine. So sine to cosine, 150 equals 150 cosine 377t plus, so plus 90 degrees. Wait, to get it to cosine, no, it'd be a subtraction of, wait, no, it'd be plus 90 degrees, right? Cosine plus 90 degrees, 140 plus 90, that's going to be 230 degrees, right? Okay, yeah. Let me verify that function. Let me verify that relationship. So cosine of t equals sine of t plus 90 degrees. Indeed. Okay, indeed. So it'd still be negative. So minus 150 cosine 377t plus 230 degrees. Sure, that works. All right, fantastic. Beautimous. Okay, and then now we're just doing a simple subtraction. Let's convert it into rectangular phase form. All right, let's do that. So we'll say y1 equals right, it'd be 250 cosine, right? Okay, so let's just say 250 phase 30 degrees. Y2 equals negative 150 phase 230 degrees. 230 degrees. Yes, 230 degrees. Okay, fantastic. So y1x equals 250 cosine 30 degrees, which is half. Yeah, it'd be no. That's square root of 3 over 2. Yeah. Cosine y2x equals 250 sine of 30 degrees. That's half. Equals 250 square root of 3 over 2 equals 250 times half. Okay. I just had to throw it in there. You know what I mean? If you got it, you got it. You know what I'm talking about. You got it, you got it. You know what I'm talking about. Okay. Next. Alright, y2 x equals, you already know where we're going, negative 150 cosine 230. I don't know what that is out the top. y equals, I labeled that x. Come on, buddy. y equals negative 150 sine 230. I'm gonna have to calculate that one on the calculator. Alright, so y1x, or we'll just say y1 equals now, and then y2 equals. Alright, we put it into a rectangular form. So 250 times cosine 30 degrees, 216.5 plus 250 sine 30 degrees, 125 j. Don't forget the imaginary number. Alright, here we got negative 150 times cosine 230 equals 96.42 minus, maybe plus, negative 150 sine of 230 plus 144.9 j. Okay, there we go. All right, so we have our two equations wrote in rectangular polar form. Wait, no, no, I'm fucking stupid. Rectangular phase form. Okay, we got phase rectangular form, whatever the shit you want to call it. All right, whatever you want. Fucking dippity doo dah yippity yay. You know what I'm talking about? All right, that's where we're at. Come inside. It's fun inside. Mickey Mouse. You know what I'm talking about? Okay. Alright, y1 equals this. Now, what are we doing? We're just doing a subtraction. Alright, a subtraction. So, we took the minus, so now we're just doing an addition. The minus, the negative. The negative. Okay, so I implemented the negative, and this all became positive. So therefore, yeah, I don't know, I guess let's just add them. Yeah, okay. Let's add them. Because I did implement the negative, and so it must be accounted for. Okay, so 216.5 plus 96.42. So 312.92 plus 144.9 plus 125. 269.9. J. Okay. So now we have that. That's our y. That's our total equation here. Okay, let's go ahead and figure for polar form. Let's turn it into polar form. Right now this is rectangular. So that's going to look like the square root of 312.92 squared plus 269.9 squared, angle inverse tangent 269.9 divided by 312.92. Yeah, I'm gonna write it down here. Equals, okay, square root of 312. Come on, can you see that? No, not quite. Square root of 312.92 squared plus 269.9. Whoops. Squared equals 413.24. Phase inverse tangent function of 269.9 divided by 312.92. 40.78 degrees. Okay, let me see. That'd be it. Yeah, that'd be it. No, that's not right. So is it a subtraction? So let me see what I would get if I did this. Let me see if I did 216.5 minus 96.42. 96.42, so 120. 120.08. Okay, plus 125 minus 144.9. Okay, be a negative minus 19.9. Oh shit. Minus 19.9 j. Right, that's our imaginary portion of the equation. Okay, so we have that. Let me see. So if we did a subtraction, okay, this is the result of the subtraction. So now we do the square root of 120.08. Oh, let's just call it 120. Minus, squared plus 19.9 squared equals 121. Nah, I messed something up here. It was a subtraction. Let me get rid of these and redo this. Bear with me, okay? I'm not happy either. I'm not happy either about it, okay? So please bear with me. All right, don't get pissed off. I'm not happy either. Rather, I'm livid. I'm actually livid. I'm burning up inside, but I'm not going to show it right. I'm going to remain cordial in the stream, okay? Professional, all right? Because I'm a professional. All right, so I'm not going to fucking freak out, okay? It's all good. It's all right. I'm not worried about it, you know? I'm not thinking about, just absolutely tearing everything apart right now. Using my nails to just get in the creases and open shit, just rip it open, just get inside, maybe chew it up. Like a dog, just chew it up and rip it up and tear it up. No excuses for the homework though, you know what I mean? Still gotta get it in. I got salt, you know, I got some salt, and I got some good, got some real quick fuses, you know what I mean, so. Oh, thank you, Dino. Thank you for the motivation. Oh my goodness, okay. I just got it refreshed. I'm ready, alright, I'm not tripping out anymore. Okay, thank you, Dino. Alright, we're back at it. Alright, so we're gonna keep this positive and let's do a calculation again, right? It is 150. I have all these numbers correct. 150, it is sine. And we did that, and we did the addition. There was no more to be done. Hold on, I gotta answer this. Streaming. I'm streaming right now. That's what I'm doing. Gosh, the audacity of some people. The audacity of some people. Okay, are you kidding me? Let me get it in. 150 multiplied by cosine of 230 degrees. Okay, negative 96. So it's just okay. Whoa. Oh, okay. What the shit? I don't know what's happening right now. Let me see something. Okay. Really appreciate you guys being here. Thank you. I love you all. I love you all so much. I love you, Donna. Uh-oh, I think, is my phone dying? No, it's on. Alright, what's happening here? So, 250 cosine. I have those correct in there. Cosine, negative 150 sine 377 t plus 140 degrees. It would be a sine thing, so I'm still not getting the correct answer. Did I miscalculate something here? Let's try this again. So 250 cosine 30 degrees. And now there's no shift here because we're already working in cosine, right? 216.5. Indeed. 250 sine of 30 degrees, right? We get 125. Okay, that's good. 150 cosine 230 degrees, right? So it's negative. So yeah, it's gonna become positive regardless. 140 plus 90 is 230. Yes, 230. Okay, so that should be correct. 96.41, 96.42. And then we have 150 sine of 230 minus 114.9 J. Okay. And again, if I do, so we're going to add them. So 216.5 plus 96.42. 312.92 plus 125 plus 114.9. 239.9 J. Right, and we do 312.92. Okay, wait, square root 312.92 squared plus 239.9 squared equals 394. Alright, well, I guess let's ask AI. I mean, I have to get I gotta get the answer, you know what I mean? So, let's fucking ask AI. I'm not gonna ask him anymore though. I have more questions here, and I'm only gonna ask him about this one because this is absurd. I mean, I'm doing it correct. Like, obviously I'm not, because I'm not getting the right answer. But all of my method is correct. Like every step to my method, I'm just missing something. Something so minute. I know it. Alright, step-by-step solutions to combine the sinusoidal functions to a single trigonometric expression using phasors. Right, convert it into phasor form. 500, angle negative 60. Negative 60. 140 minus 90. No. Wait, maybe it read it wrong. Wait. negative 500 cosine, negative 60, 100 oh, that's part A. That's part, or whatever. Okay, part B. This is the one. This is the one. Alright, so it did subtract it. It did subtract it. Minus 90. What the fudge? Sine equals cosine minus 90 equals cosine minus 90. Okay, I gotta get that down. I don't know, that shit, I just can't quite get the relationships, like, absolute, not absolute. So that's my problem. I just didn't do subtraction. I did an addition of the phases. So yeah, that's totally gonna ruin everything. I done fucked up, I ain't gonna lie, but there it is here. Oh, you can read it for yourself. Take a look at this now. Right, so this is the relationship that I was messing up. Right here, sine phi equals cosine phi minus 90 degrees. So now, if we apply that to what we have going on here, I will show you that we will get the right answer. Okay, so cosine 30, this is where we fucked up. Right here, fucked up. Right here, fucked up. It's going to be 140 minus 90 because sine phi equals cosine phi. Cosine phi minus 90 degrees. All right, we really need to imprint that into the mind. We need to never forget it. All right, traumatize me with it. Traumatize me with it. Traumatize me with it so that I never forget it. Okay. Hang on to it. All right. All of this is wrong. This side should all be correct because we don't have that minor addition. So 140 minus 90 give us 50 degrees, right? 50 degrees, 50 degrees, 50 degrees, 50 degrees. That's wrong. That's wrong. 50. Alright, so now 150 cosine 50 degrees. Y2 equals 96. We didn't do the weight, so no negative though, right? No negative this time. So 96.41, 42, 96.42. Plus, maybe a plus, maybe a minus 150 sine of 50 degrees plus 114.9 J. So 216.5. Cosine 30. Yeah, so 216.5 minus 96.42. So 153.08 plus maybe. No, it's going to be a minus 125 minus 1. Oh, no, well, it'll be positive 0.4. 10 plus 10.1 J. Okay, right, so the magnitude of this is going to be, so Y is going to equal square root of 153.08 squared plus 10.1 squared, and the square root of that 153.41. What the fuck? That still ain't right though. 250. Yeah, that's what I got. Negative 96. Whatever. If you do plus, okay, so negative 130 degrees. Okay, well, it goes through a step to eliminate the negative sign, but well, what is the purpose? I mean, what is really the purpose of that? Is that absolutely necessary? 96. Okay, so the same thing. They got fucking 120 and 10. Wait. 153. Okay, I made a huge mistake. Where did I even get that number? I did 216.5 minus 63.42. Where is 63.42? Does anybody see that number in here anywhere? I continue to surprise myself. Like, truly, truly amazing. Imagine being pissed off at yourself. Imagine that, because that is what I feel right now. What an idiot. 96.42, 120.08. Again, plus, that was correct. Let me recount. Well, 10.1. J. That's correct. Okay, so y equals the square root of 120.08 squared plus 10.1 squared equals 120. This is correct. 0.05. Or, yeah, 120.5. Plus, phase. And again, remember inverse tangent, so, inverse tangent of 10.1 divided by 120.08. Really? Nah, for real. That's really it. Yeah, it is. 4.8 degrees. Yeah, that's really it. Okay, so to write it in time-dependent form, y of t equals 120.5 cosine omega t, which omega is 377 t plus 4.8 out of 0 degrees, like that. Beautimous, absolutely beautimous. I really appreciate y'all being in here. Thank you. You are the absolute best. Give me a follow. I also stream on YouTube as well. You know, whatever your forte is, whatever your niche is. But you know, if you guys also do stuff, you know, please comment. Leave a comment in the chat. Go ahead and @ your channel. I don't care about soliciting. You know, you can go ahead and solicit your shit all you fucking want. I don't think anybody's gonna buy it, right? Unless it's very good. You know, who am I to judge? So don't let me put you down by any means. But you know, if you do something creative as well, you know, leave it in the chat. Let's do a little follows, do a little mashup, a little networking. You know what I'm talking about? Think about this. It'd be very good. Okay. I don't know. What should we move on to the next, or should I just like call it? Kind of getting there. Kind of getting to the point where I think I might just call it. We did a lot. We did a good bit. How long have we been going? We've been going for an hour 43. It's almost 2 hours. That's probably pretty good, right? It's 9:50. It's almost 10. Yeah, I'm going to call it a night. All right, cool. I really appreciate you guys being here. That was fucking excellent. We got through a lot of work. I hope some of this is informative. Perhaps you can reflect back on this and use it to help you understand your circuit analysis, or, you know, if you want to be a hobbyist in electronics, this is very beneficial. Or if you just enjoy the entertainment, let me bring that aspect, right? Let me be the entertainer, as I am trying. I'm trying very hard. You know, perhaps there's a comedic value to it that I could bring to the table, but I am the table. You know what I'm talking about? I am the fucking table. So, you know, don't play with me. Put some respect on my name. And absolutely, until next time, I really appreciate you guys being here again. And follow me for more content. I'm about to do some more stupid shit. We're going to get into high voltage. You know, it's going to be a lot of fun. You'll probably see me get hurt a couple times. Let's do it. Bang. Right there. Entertainment. Fucking, I'm watching the gladiators in the Coliseum.